Now I want to run another one sample test. Rather than testing to see whether these teachers serve more than 100 students throughout an entire school day, I'm going to go back to the average class size and see if their class sizes differ than the national average of 25:1. So again, compare means. I have one sample, all the teachers in this district, and one value, the known value of 25:1. So I'm going to remove total number of students and I'm going to drag back over class size and I'm going to change my test value to 25. So this is essentially saying, does the mean of this class size from all these teachers in these 5 districts, is it different enough from 25:1, the known value for the nation, to be considered statistically different? So I click OK, and here's what I get. 1,512 teachers in these 5 districts answered the question, what's your average class size? And it's 21.8 with a standard deviation of 7.35. So I go down to my actual one sample test. I see the test value of 25:1 students. I see that the mean was 21.8 from my sample. So I go 21.8 minus 25 gives me a mean difference of negative 3.187. And is that far enough from 0? The mean difference would be 0 if my mean was also 25:1, which wouldn't be different from the known value, so it would be insignificant. But I go over and I say this mean difference gives me a significance, a p-value of 0.000, which is less than 0.05. Therefore, I conclude that teachers in these 5 districts serve average class sizes 21.8, which are significantly lower than the known national average of 25 students to 1. Now, I want to draw a picture, because a picture's worth 1,000 words sometimes, to show you what that test just did. And I'm never going to ask you to memorize a formula, but I want you to conceptually understand the test. So here we looked at, does the mean class size of this sample of teachers differ from 25 per class? Our null is no. A t-test formula is simply, t is the observed mean, which in my case was 21 point something. I don't know, we just ran it, 21.3 or something like that. It's the observed mean minus the known mean, which was 25, all over what's called the standard error, estimated standard error. And estimated standard error simply equals the standard deviation over the square root of n minus 1. So I have the observed mean minus the known mean, all over the standard deviation divided by the square root of n minus 1. So why is that an important formula? What we did when we ran this test, let me flip back and pull up the actual output. What we did was we said with a 95% confidence interval, the lower mean is negative 0.3, the lower t, lower bound, is negative 3.57, and the upper t is negative 2.82, the upper bound. With an alpha set at 0.05, 95% of all the t values fall between negative 3.56, and negative 2.89. That's what the alpha of 0.05 is. If I set an alpha of 0.1, this would give me a 90% confidence interval around the mean, and it would be even wider. So what we did was we said, we got a mean of 21.81, and the known value was 25, which led to a mean difference of negative 3.187. Is this number far enough from zero to conclude that my class sizes in this district, the average class size, is different than the known value of t? So let's think about that. If t was based on the observed mean minus the known mean, and you had a class size of 25, and the known mean was 25, your t would be 0, and that's not going to reject anything. So we want a bigger numerator, either positive or negative. So the further we get away from 25, the bigger our t gets. It goes out further, and we want to get past the values that contain 95% of all the t's so that we can reject the null. So a bigger difference between the two means gives me a bigger t value, so you're more likely to conclude there's a difference and reject the null. But the denominator matters as well also. We have a standard deviation of 7.35. The bigger the standard deviation gets, the bigger the denominator gets. So as your standard deviation goes up, the t decreases. Something bigger in the denominator divided by a bigger number makes it smaller. So in practical sense, what that means is the more variance or standard deviation we have in our distribution, the less comfortable we are that our mean actually represents our sample as a whole. So you can get a mean of 50% correct on a test because half of the students made a 0 and half made 100, or all made a 50. The one that's all made a 50 is more representative of the real known population. So as we become more comfortable that our mean really represents our true mean, our standard deviation goes down and our t-value goes up. But sample size also matters. So let's think about this with easy math. Let's say that our n size is only 10. And our standard deviation equals 9. 10 minus 1 is 9. The square root of 9 is 3. Standard deviation of 9 divided by 3 gives you 3 in the denominator. Now let's say we made our n 101. So 101 minus 1 is 100. The square root of that is 10. 9 divided by 10 gives you 0.9 in the denominator. So what does that mean? As our n size goes up, what's happening to the t? We're getting a bigger value. T is going up. It's almost like thinking of a double negative, right? It's dividing the standard deviation, which is making it smaller, the denominator smaller when this is a bigger number. When you make the denominator as a whole smaller, your t goes up. So as we increase our sample size, we make the denominator smaller, therefore our t goes up. And that's my example of, did I flip the coin 10 times or did I flip the coin 15,000 times? So there are three things that really affect your results here. The first one should be very obvious. How far away is your mean from the known mean? The further they are, the more likely they are to be different. How's that reflected? You get a bigger t-test. Secondly, how sure am I that all my scores really represent the mean that I used here? Bigger standard deviation means I've got more error, I'm less comfortable. So bigger standard deviation raises the denominator, lowers the t. Third factor is sample size. As I have a bigger sample size, I shrink the denominator and raise my t because I flip the coin more times and I'm more sure that I'm representing my sample. So let's look at this problem that we just charted. I got a mean value, 21.81. 21.81 minus 25, all over my standard deviation of 7.35 over my square root of n minus 1, 1512 minus 1, which is 1511, which is just a fancy way to calculate the standard error of the mean. So that is really my denominator, 0.189. And that yielded a t-value of negative 16.858. 21.81 minus 25 gives me a mean difference of negative 0.319 all over my standard error of the mean, 0.189, which gives me my observed t of negative 16.858. So I look at my observed t of negative 16.858 and I say, is it between negative 3.56 and negative 2.89? No, it's way past. So I say this mean is so far away from 25 that it yields a t-value outside of my upper and lower bound t-values. So I reject the null and I say teachers in this district serve students with lower class sizes than the national average of 25. So what we can do here is we can think about this picture more and we can say, I got a value, alpha, I set it at 0.05, so that's a 95% confidence interval, which gives me my upper and lower t's. And I got a significance value of 0.000, which is obviously way less than 0.05. Well, that also tells me something here. What if I got a p-value of 0.049? That's still less than 0.05. So I would still reject my null, but barely. I barely have a mean difference that got past the t because my significance value got closer to 0.05. So they're significant in both cases. They yield the same interpretation, but the fact that I have a 0.000 tells me I rejected it by quite a bit. If I got a p-value of just barely rejecting it, my observed t would fall here. If I got a t-value of greater than 0.05, but barely, I fell just inside. If I got a t-value of 0.999, I'm right smack in the middle, and there's no way it's even close to difference, so my mean would have been something like 24.98.